Hello. So in this lecture I'm mostly going to talk about relations and equivalence relations. But in this first part of the lecture I just want to spend a little bit of time introducing some notation. Because maths is all about making very clear statements and connecting them logically to each other. And I just want to introduce some notation that we use to help with that logic. This is something I'm going to talk about more in a future lecture, but I'm going to start using some of it, so I'm going to introduce it now. So I'm going to say that we deal with lots of logical statements, or sometimes we call them assertions. So for example, some kind of really straightforward ones might be to say things like n is equal to 2. That's an assertion. Or I could say n is even. Those are obviously very straightforward statements. We have more complicated ones. So let me write out this one. There exists x, y, and z in the set of positive integers. So you'll see various kind of decorations of these letters that mean different things. So this with a plus sign means it's a set of positive integers, such that x cubed plus y cubed is equal to z cubed. Okay, so there's another assertion. Okay, and we have to connect these kind of statements logically to each other. And in order to discuss how we do that, we often give the statements names. We give them a letter. And we've seen examples of this before. It seems to be conventional to denote them by P and Q. So let me suppose that this one is the statement P, this one is the statement Q, and then this one can be the statement R. And we have to be able to deal with these things whether or not they're true. So it's quite helpful to be able to deal with statements that turn out not to be true. If we can work through the logical consequences of a statement, we might end up showing that it doesn't make sense. That's what happens in a proof by contradiction. So we have to be able to work with them whether or not they're true. And in this case, the first two statements here, the P and the Q, depend upon n. In fact, sometimes we write those as P of n. We did that when we were doing proof by induction in the first lecture. So whether or not P and Q are true in this case would depend upon n. The statement R here doesn't depend on anything. It's just a statement, and it's actually false, as you may be aware. And that's Fermat's last theorem. But we have to be able to work with these statements, whether they're true or false. So one thing that we might do is try and combine statements. And we might also try to negate them. I'll say what that means in a second. And we have a bit of notation that is sometimes used to help with this. So combining them, we could say P or Q. And this notation means P or Q. In other words, either P is true or Q is true. We write P and Q to mean P and Q. And we write not P to mean not P. So let me just go through these in these examples. So P or Q, when P and Q are defined as they are here, P or Q, well, that would actually be equivalent in this case just to n being even. P and Q, well, that would be equivalent to n is equal to 2, if both P and Q have to be true. And not P, that would be equivalent to saying n is not 2. So that's called negating the statement, saying that the statement is not true. Not Q in this case, that would be that n is not even, at least strictly that's what it would be. Often in these cases you have to use a bit of common sense. So the fact that we were talking about the thing being even, and the fact that it was written as n, kind of suggests that we're thinking of n as being an integer. So you might equally say that not q is the statement n is odd. So we have to use a bit of common sense in thinking about the context. And not r, in this case, well, not r is true because r is false. So not r means there does not exist positive integers x, y, and z, such that x cubed plus y cubed is equal to z cubed. I realise that even here is not written very well, so let me just write that bit better. N is even. That should have said. So personally, I don't really like these symbols. I just write out or, and not. But you will see these symbols getting used sometimes. And there is a completely direct analogy between or, and not, and the set, union, intersection, and complement that we were talking about in the last lecture. You may have noticed when we talked about the unions, if we said x is in A union B, then that means x is in A or x is in B. And the symbols even look very similar, at least for the intersection and the union. So I'm just going to say here there is a direct analogy between or and not and union, intersection, and complement. And in particular, that means that the way that you manipulate these and, or, and not is basically the same as the way that we manipulate unions, intersections, and complements. And the one that I particularly want to emphasize is De Morgan's laws. So they be a sort of logical equivalent version of De Morgan's laws. And so let me just write those out. That basically just tells me how to negate a statement that includes an and or an or. So if I want to say, and I'm going to write this with just with words, if I want to say that we don't have P or Q, that's equivalent to saying that we don't have P and we don't have Q. When I say we don't have P, I mean P is not true. Okay, and not P and Q, that's equivalent to not P or not Q. Right, so the not can kind of come through the brackets, but it changes the and into an or and the or into an and. And this is, if you just think through the logic here, this is just common sense. But if I don't have either P or Q, then that means I don't have P and I don't have Q. Okay, but when we're dealing with more complicated statements, this can actually end up being a bit confusing, and sometimes it might be helpful just to come back and really stick rigidly to these laws. Okay, so I want to introduce a bit more notation. So I'm going to say we write P implies Q to mean P implies Q. So this is a double-lined arrow. Equivalently, that statement means the same thing as saying if P, then Q. By which I mean if P is true, then Q is true. And you're going to see that kind of phrase coming up a lot. So in the example that we just had, P was n is 2, Q was n is even, then indeed P implies Q. But in that example, Q does not imply P, so this does not say anything about P needing to be true if Q is true. But obviously that in some other situation that might be true, and so we have some notation for that too. So we write P if and only if Q to mean that P implies Q and Q implies P. Or the way that I just read it, in fact, P if and only if Q. Right, and as I said, I think in the last lecture, if and only if is a phrase that you'll keep coming across. Another way that I sometimes read this double-headed arrow actually is P is equivalent to Q. And sometimes I find it more convenient to read it that way. So this could also be read as P is equivalent to Q. If and only if, some people shorten if and only if to IFF. I don't tend to do this, but some people write if and only if as IFF, if. Okay, and then the last thing I want to mention is some things called quantifiers. And these are really just shorthand notation for a couple of things that I've already had to write out quite a few times. So we're going to write this symbol, a kind of upside down A, to mean for all. So you might have noticed I've had to keep saying things like for all natural numbers, for all n in the natural numbers. So we can now write that as for all n in the natural numbers. Sometimes it's better to read it as for every, just depending on the context. Okay, and then another one is there exists, which we write as this backwards E. So that means there exists. So we might say something like there exists x in the real numbers such that x squared is equal to 4, say. And different people have different ways of writing this. So typically if you say there exists x in the real numbers, you then say such that something is true. Because if you just say there exists x in the real numbers, you're not really saying anything, you're just saying the real numbers is a non-empty set. So I tend to write ST standing for such that. You'll find some people don't write that. Some people kind of assume that the such that is kind of implied by the just writing the there exists symbol. Some people would put a colon here, and you've seen me using a colon to mean such that in the context of writing out definitions of sets. Personally, I tend to write such that. And the reason I do that is because I want to try and be able to read statements like this as a sentence. So this is where maths is starting to become its own language. So I want to be able to read this as there exists x in the real numbers such that x squared is equal to 4. Okay, so this statement, this thing here, the for all symbol, is called the universal quantifier. I just want to make a note of this. This one is the universal quantifier. It's saying that something is true for all objects in some set. And this one is called the existential quantifier. It's saying that there exists something. There's one variant on these which I don't tend to use, but you will see, and that is if we write there exists exclamation mark, that means that there exists a unique element that has this property. So that means there exists unique. So for instance, we couldn't have said that in the example I just gave, but we could say there exists a unique x in the real numbers such that x squared is equal to 0. Okay, let me just give you a brief example of how we can use this to help streamline things a bit. I'm going to give you an alternative proof of the double inclusion principle that we did in the last lecture. So remember that this was the statement that two sets A and B are equal if and only if, which I'm now going to write with this arrow, A is a subset of B and B is a subset of A. It was this quite obvious statement. So here is an alternative proof that we use a bit more of this notation. So two sets A and B are equal if and only if every element of A is an element of B. So I can write that as A is equal to B. That's equivalent to saying, so I'm going to write that like that, that for every x in S, remember A and B are subsets of some larger set S, x is in A if and only if x is in B. And this has become a bit hard to read, so I'm going to put some brackets around here to clarify the way I was supposed to read that. So A is equal to B is equivalent to saying for every x in S, x is in A if and only if x is in B. And then I'm going to say, well, that's equivalent to saying something else. That's equivalent to saying that for every x, x is in A implies x is in B, and x is in B implies x is in A. That's really a definition of what this if and only if symbol meant. But then now, this statement here, x is in A implies x is in B, that is exactly the statement that A is a subset of B. And this is the statement that B is a subset of A. So this is now equivalent to saying that A is a subset of B and B is a subset of A. And therefore we have shown that A equals B is equivalent to A being a subset of B and B being a subset of A. Okay, so we can make some proofs look slightly more slick by using some of this notation. Okay, so let me just remind you what we've done there, and we will take a pause. So we've said that we can combine logical statements with and ors and nots. We've said that in order to do the negation, the not something, we can use De Morgan's laws. And then we've introduced the implies, if and only if, for all, and there exists. And I'm going to start using this notation sometimes. I'm now going to talk about relations. So these are things like less than or equals to, which compare two objects in a set. So I'm going to start with a definition. So we're going to say a relation, which will denote R. Typically we're going to relate two objects that are in the same set, but we can relate objects in different sets, and I'm going to write down a definition for that, a more general case. So I'm going to say that the relation is on sets A and B. And the way we define it is going to seem slightly strange, but we're actually going to define it as a subset of the Cartesian product A cross B. So remember, the Cartesian product was a set of ordered pairs, so like A, B, where A is in A and B is in B. And if an element A, B is in that subset R, then we're going to write that A is related to B, which we write as ARB. And so I'm just going to make the comment here that often A and B are going to be in the same set. So let's just look at an example. I'm going to make this a bit easier by making the sets quite small. So let's take A and B to be the same set, and I'm going to take them to be a set with elements 1, 2, and 3. So it's a subset of the natural numbers. Then we're going to define less than or equals to, which we kind of know how to define. We talked about that in the first lecture. But with this definition, as a relation, this is going to be defined to be a subset consisting of ordered pairs, and it's the ordered pairs for which the first element is less than or equal to the second element. So it's going to include 1, 1, because 1 is less than or equal to 1. It's going to include 1, 2, and it's going to include 1, 3. It's also going to include 2, 2, 2, 3, and 3, 3. Right, it's all of the pairs where the first number is less than or equal to the second number. And so with this formal definition, that would be what less than or equal to sign is. But we write, according to this, A is less than or equal to B. So there's quite a few relations where we don't write R because the relation is so important that it has its own symbol that's been associated with it. So obviously less than or equal to, we use a less than or equal to symbol. Another example of a relation would be equals. And I'm going to struggle with my notation here. So equals as a relation is this subset which includes 1, 1, 2, 2, and 3, 3. Okay, let me give you an example where the sets A and B are not the same. So let's suppose that S is the set of students at Oxford, and C is the set of colleges. And then I'm going to define a relation on S and C. So say then we define R such that for any S in S and C in C, S is related to C if and only if, I'm going to use that symbol now, S is a member of C. Right? So a student is related to a college if they're a member of that college. Okay, let me define some properties that these relations might have. So I'm going to let S be a set and R a relation on S. So we're just, this is going to be a set related to itself. Then I'm going to list 4 properties that they might have. So the first one is going to say that R is reflexive, and this means that X is related to X for all X in the set. Right, so if that's the case, then it's called reflexive. The next one is that R is going to be called symmetric if whenever X is related to Y, then Y is related to X. Right, so the relation works both ways around. For all X and Y in S. I might just try and squeeze in here that same thing written in terms of this symbolic notation that I was just talking about. So we could have written this as for all X and Y in S, X is related to Y would imply that Y is related to X. That would be a symbolic way of saying the same thing as whenever X is related to Y, then Y is related to X for all X and Y in S. Right. So you're going to see quite a lot of this sort of more condensed way of expressing things. The third property that R might have is being anti-symmetric. And so that is the case if whenever x is related to y and y is related to x, then x is equal to y. So with this property, the only way you can have x related to y and y related to x is if x is equal to y. Okay, and the final one is going to be transitive. So R is transitive if whenever x is related to y and y is related to z, then x is related to z. So that's what it means to be transitive. So let's just look at some examples to see that. So let's take the less than or equal to sign on the set of real numbers. So is this reflexive? Yes, it is, because x is less than or equal to x for any x. So this is reflexive. Is it symmetric? Well, no, it's not symmetric, because if x is less than or equal to y, then that doesn't mean that y is less than or equal to x. It means the opposite. So this is not symmetric. Is it anti-symmetric? So if x is less than or equal to y and y is less than or equal to x, then that does imply that x has to be equal to y. And that was the definition of being anti-symmetric. So it is anti-symmetric. And it is transitive, because if x is less than or equal to y and y is less than or equal to z, then x is less than or equal to z. Let me give you another example. The not equal to on the real numbers. So not equal to is an example of a relation. It's a slightly confusing one, but it is an example of a relation. And it is not reflexive because x is equal to x. So x is not equal to x. So any element is not equal to itself. So this is not reflexive. Is it symmetric? Well, yes, it is symmetric, because if x is not equal to y, then certainly y is not equal to x. So it is symmetric in this case. Is it anti-symmetric? If x is not equal to y and y is not equal to x, does that imply x is equal to y? Well, no, that would be complete nonsense. So it's certainly not anti-symmetric. So it's not anti-symmetric. And then transitive. So if x is not equal to y and y is not equal to z, does that imply that x is not equal to z? Well, no, it doesn't, because x and z could be the same there. X not equal to y, y not equal to z. It could be the case that x is equal to z, so then x would not be related to z. So this is not transitive. Okay, so as I said, that one is slightly confusing. I just want to point out, this is not hugely important, but it is something that is just worth knowing the definition of. If you've got something like this less than or equal to sign, which is reflexive, anti-symmetric, and transitive, then it's called a partial order. So I'm going to write down a definition. A relation R is called a partial order if it is reflexive, anti-symmetric, and transitive. And it can lead to an ordering. It's called a total order. If, in addition to that, for any x and y in the set, either x is related to y or y is related to x. So the less than or equal to sign would be a total order, because it does have this property that one or other of those two relations must hold, or in fact both of them, if x is equal to y. And so that then leads to an ordering of the set. So we talked about this in the context of the natural numbers, and the same thing works in the context of the real numbers as well. An example of something that would be a partial order but not a total order is the relation divides. So I'll just give this as an example. The relation divides on the natural numbers, which we often denote with a vertical line, is an example of a partial order that is not a total order. Okay, I'll leave you to check that that satisfies the definition of being a partial order. I want to give another example, which is going to lead me on to talking about equivalence relations. So this is another example of a relation, and it may be one that you've seen before. I'm going to let n be greater than or equal to 2 and define a relation R on the set of integers z by saying that A is related to B if and only if, I'm using that symbol again, B minus A is a multiple of n. And so you might have come across this before. This is congruence modulo n. And it's the basis for modular arithmetic. So which of these properties that I listed on the previous slide does this relation have? This one, is it reflexive? Well, yes, it is reflexive. That means A is related to A for every A. And that's true here because A minus A is 0, which is a multiple of n. So it is reflexive. And it is symmetric, because if A is related to B, that means B minus A is a multiple of n, and that means that A minus B, which is the minus of that, is also a multiple of n. So it is symmetric, and it's also transitive. And maybe I'll just write out a bit more to explain why it's transitive. If we're transitive, we want to try and show that if A is related to B and B is related to C, we want to try and show that that implies that A is related to C. But by the definition, if A is related to B, that means B minus A is a multiple of n. So let's write it as k times n for some integer k. And B is related to C means that C minus B is some multiple of n. Let's call it L times n. So for some k and L integers. And then if I add those together, you can see I'm using this implies symbol here to say that one statement implies another one. So this then implies that C minus A is k plus L times n, which is a multiple of n. So that implies that A is related to C by the definition of the relation. So indeed it is transitive. Okay, and Any relation that has these properties of being reflexive, symmetric, and transitive is called an equivalence relation. So this is an example of that. So I'm going to write out a definition now of an equivalence relation. But in fact, I just said it. So this is the definition of an equivalence relation. I'm going to say a relation R on a set S is an equivalence relation if it is reflexive, symmetric, and transitive. And this is probably the most important thing in this lecture. It's something that you're going to come across quite a lot, is the idea of two elements being somehow equivalent to each other. And so the way that we can systematically come out with a definition of things being equivalent is by defining a relation between them which has this property of being reflexive, symmetric, and transitive. Okay, and if the relation is an equivalence relation, then we tend to use a different symbol for it. We use a tilde. So we write it as tilde. And you'll see examples now. So let me give you some examples of equivalence relations. And the first one is going to be the example that I was just talking about of congruence modulo n. So if S is the set of integers and the equivalence relation is congruence modulo n. So that is an example, and actually this one is special enough to have a different notation again. Typically we write, instead of writing A is equivalent to B, which I sometimes read as A twiddles B, in this particular case we often write that as A is equal to B mod n. Right, and you might have seen that before if you've worked with modular arithmetic. So that's one important example of an equivalence relation. Let me give you another one. Suppose S is the set of complex numbers, and we define an equivalence relation by saying that two complex numbers Z and W are equivalent if and only if their moduluses are equal. So that defines all complex numbers that have the same modulus. So you think of those as points on a circle in a complex plane. They're all equivalent to each other according to that equivalence relation. If I took S to be the set of polygons in R2, and then I could define equivalence relation as two polygons being equivalent if they are congruent. So let's say the equivalence relation is in that case congruence, meaning that two polygons are equivalent if one of them can be translated and rotated into the other one. One more example that I'll give you, which might not make a lot of sense, but it's something that's quite important in algebra, is if S is the set of matrices, I'm going to take it to be Mn of R is the set of n by n matrices with real coefficients. And the equivalence relation is something called similarity of matrices. And so let me just explain what that means. I would say that two matrices A and B are equivalent if and only if there exists an invertible matrix P such that A is equal to P inverse times B times P. That's the definition of A and B being similar matrices. Okay, so as I say, this might be a bit alien to you at the moment, but it's something that you will see in, actually probably both in linear algebra and maybe in geometry as well. So this is getting at the fact that if you try and represent a matrix in a different basis, then you can relate the old and the new matrices in this way. And those matrices would then be called similar matrices, and they're kind of encoding the same information somehow. Okay, so I'm going to give you another definition now. There's lots of definitions here. And this is of an equivalence class. So I'm going to say, given an equivalence relation tilde on a set S, and given a particular element of that set, so an element X, say, in S, we're going to define the equivalence class of that X we define that as the set, and we denote it X with a bar over the top of it. X bar, it's the set of all elements of S that are equivalent to X. So I'm going to write that as the set of all Y in S such that Y is equivalent to X. So hopefully that makes sense. And in the context of this congruence modulo n, for instance, the equivalence class of 0 is the set of all multiples of n, so 0, n, 2n, 3n, and so on. So the equivalence classes give you a way of grouping together all the elements that are equivalent to each other according to the equivalence relation. Okay, and now the last thing I want to do is to just say something about how this relates to partitions of a set. So I'm going to define a partition. So this will be a partition of a set S is a collection of non-empty disjoint subsets whose union is S. Okay, basically it's just a way of taking the set and cutting it up into different parts. The parts have got to be non-empty and they've got to be disjoint, so they can't overlap. And if we add all of the parts together, we've got to get the whole of the set S. So let me just write I hope that makes sense, but let me write a sort of algebraic way of writing that. The partition is going to be a collection of subsets. So I'm going to write that as AI for I in some indexing set, such that AI are not the empty set for all I. Their union has got to be S, so we're going to say the union over all I of the AI has got to be S, and they've got to be disjoint, so I'll write that as AI intersect AJ is empty whenever I is not equal to J. Okay, so you can use a partition to define an equivalence relation, and that's why I'm talking about it here, because we can say that two elements of the set are related and they're equivalent if they're in the same part of the partition, so if they're in the same one of these subsets. So I'm going to say, given a partition of a set S, we can define an equivalence relation tilde by saying that x is equivalent to y if and only if x and y are in the same part of the partition, so in the same subset. Okay, and I will leave you to check that that satisfies the properties of being an equivalence relation. So it's got to be reflexive, symmetric, and transitive. Let me just give you an example, quite a straightforward example, going back to a set of students. So if S is the set of Oxford students, then we can partition it according to the colleges that they're at. So the subsets are the sets of students at each college, and that forms a partition because none of the colleges have got no students. You can't be a student at more than one college, so these subsets are going to be disjoint, and all students at Oxford are a member of a college, so the union of all of those subsets will be the whole set of students. And then if we use the equivalence relation that's induced by that partition, we would say that a student X is equivalent to a student Y if they're at the same college. Okay, one last thing I want to give you is a proposition. And that goes the other way around here, and that's to say that if we have an equivalence relation, then the equivalence classes, which I just defined, are a partition of the set. So I'm going to say, given an equivalence relation, tilde on a set S, the equivalence classes form a partition of S. And that's something that you're going to prove, I think, in the groups course, which will be later this year, although it's actually quite straightforward, so if you want to have a go at it, you can. Okay, let me just quickly summarize what we've done there. So way back here. So we've defined a relation, and formally we've done that as a subset of ordered pairs. We've defined these properties of that relations might have. We've looked at a few examples, and then we've said that a relation is an equivalence relation if it is reflexive, symmetric, and transitive. And we've seen that we use this symbol to mean things are equivalent. We've defined equivalence classes, and we've defined a partition, and we've seen that equivalence classes and partitions are kind of the same thing.